This is a review of exponents and radicals from Math 10C. The exponent laws, something you need to know in Math 20-1. We have the multiplication exponent law, or the product rule, tells us that when we are multiplying the same base, x and x in this case, we add the exponents. For example, x to the power of 3 times x to the power of 3 equals x to the power of 3 plus 5, which is x to the power of 8. Power of a power tells us when we have one base and it's to the power of something, and then the whole thing is to the power of another exponent, we multiply those exponents. An example, n to the 4 to the power of 3 is n to the 4 times 3, which is n to the power of 12. The power of a product tells us that we can distribute an exponent into the brackets, and it goes to each of the terms in the product. So x times y to the power of a equals x to the power of a, y to the power of a. Example, xy to the power of 5 gives us x to the power of 5 times y to the power of 5. Power of a fraction law is really the same thing. We have a power on a fraction that can be distributed into the fraction to the top and the bottom. So x over y all to the power of a is the same as x to the a over y to the a. Example, m over n to the power of 7 is the same as m to the power of 7 over n to the power of 7. The division law, x to the power of a over x to the power of b, so we have the same base. Notice that it has to be the same base. We can write this as one base where we subtract the exponents. The exponent from the numerator has to be first, so it's numerator minus denominator exponent. Example, y to the power of 6 divided by y to the power of 2 is y to the power of 6 minus 2, which gives us y to the power of 4. The negative exponent law is how to change a negative exponent to a positive exponent. We do this using reciprocals, which we just covered. X to the power of negative a is equal to 1 over x to the power of a. So if we have a base with a negative exponent, we can put 1 over that base and then it becomes a positive exponent. Or if we have 1 over x to the power of negative a, so our exponent is negative on the bottom of a fraction, we move it to the top, we get x to the power of a over 1, which is just x to the power of a. Example, x to the power of negative 3, y to the power of negative 2. Since both bases have negative exponents, we need to move both bases. So the x needs to move to the bottom, and then the exponent will become positive. The y needs to move to the top, and then that exponent will become positive. We get y to the 2 over x to the 3. Write each expression as a power with a single positive exponent. 5 to the power of 8 times 5 to the power of negative 3. That is the multiplication law. Tells us to add the exponents. 5 to the power of 8 plus negative 3, which equals 5 to the power of 5. Y to the power of 12 times y to the power of 8, that is also the multiplication law. We get y to the power of 12 plus 8, which equals y to the power of 20. A to the power of 5 to the power of negative 2. I see two things there. I see power of a power. I also see negative exponent. There's not really a bedmass when it comes to exponent laws, but I typically leave dealing with negative exponents until the end, because sometimes they just become positive exponents through applying other laws. So I'm going to do the power of a power law. a to the 5 times negative 2, which equals a to the negative 10. I still have a negative exponent, so I'm going to take care of that. I put a 1 under my variable, and then I move the a to the 10 to the bottom, and it becomes 1 over a to the power of 10. 3 times x squared times y all to the power of 3. That is power of a product, so I can apply that exponent of 3 to each of those terms in the product. I get 3 to the power of 3, x to the power of 2 to the power of 3, y to the power of 3. Then I have a power of a power with the x. I get 3 to the 3, x to the power of 2 to the power of 3. That's power of a power, which tells us to multiply the exponents. We get x to the power of 6, and then y to the power of 3. And I could evaluate the 3 to the power of 3, but the question doesn't say that I have to evaluate, so I can also leave it as 3 to the power of 3. X to the power of negative 2 over y, all to the power of 4. With power of a fraction, I can apply that power into my fraction, which gives me x to the negative 2 times 4 over y to the 4. I do the power of a power rule, multiplying my exponents, x to the power of negative 8 over y to the power of 4. And then I have a negative exponent. I only have a negative exponent on the top. So I just want to take the top and move it to the bottom. The y to the 4 does not move because it's positive. It has a positive exponent where it is. Then I get 1 over x to the power of 8, y to the power of 4. X to the power of 5 over x to the power of negative 3. This is the division law, so I want to subtract. It becomes x to the power of 5 minus negative 3, which equals x to the power of 5 plus 3, which equals x to the power of 8. Two x to the power of 3 over 2x to the power of negative 2. So my base in this case is 2x. I have the division law, which tells me to subtract my exponents. 2x in brackets to the power of 3 minus negative 2, which equals 2x in brackets to the power of 3 plus 2, which equals 2x in brackets to the power of 5. And then I can apply that 5 into my product, the power of a product, to get to the power of 5, x to the power of 5. T to the power of negative 4 times t to the power of 3, all to the power of negative 3. I typically will take care of what's inside first. Like I said before, there isn't really a bedmass for exponent laws, but I'm going to simplify the inside first. So I have t to the negative 4 times t to the 3. That's the multiplication rule. Tells me to add the exponents. T to the negative 4 plus 3. And then that is all to the power of negative 3, which gives me t to the power of negative 1 to the power of negative 3. This is power of a power rule, so I multiply my exponents. Negative 1 times negative 3 is positive 3, so I get t to the power of 3. That's why I take care of my negatives last, because sometimes through other simplifications, you end up without negatives. The square root of a number is the inverse operation of squaring. The square root symbol is used to indicate the square root operation. This type of irrational number is known as a radical. some parts of a radical. We have the index, which is the little number that tells us which root we're taking. If there is no index, it means square root, so it means an index of 2. We have the base, which is the whatever is big under the root, and then we have the exponent on the base. Everything that's under the root is called the radicand, and the whole thing together is called a radical. Simplifying radicals. When simplifying radicals, it is best to make sure you use perfect squares and perfect cubes. So what are perfect squares and perfect cubes? They're numbers that you can take the square root of and you get a whole number. You can make these numbers by using your calculator and doing 1 squared, 2 squared, 3 squared. So 1 squared is 1, but it doesn't really help us. We start at 2. 2 squared is 4. 3 squared is 9. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, and so on. When we talk about variables, which we're going to do in the next unit, x squared, or any variable squared, is a perfect square, and also x to the 4, and x to the 6, and x to the 8, and x to the 10, and so on. So any even number for the exponent will be a perfect square. We can write this in general by saying x to the power of n to the power of 2, which would equal x to the power of 2n. Perfect cubes, same idea, but cubing the number instead of squaring it. 2 to the power of 3 is 8, 3 to the power of 3 is 27, 4 to the power of 3 is 64, 5 to the power of 3 is 125, 6 to the power of 3 is 216, 7 to the power of 3 is 343, 8 to the power of 3 is 512, and so on. We can do the same thing with variables. X to the power of 3 is a perfect cube. X to the power of 6 is a perfect cube. X to the power of 9 is a perfect cube. X to the power of 12 is a perfect cube. So any exponent that is divisible by 3 would be a perfect cube. We can write this in general by saying x to the power of n to the power of 3, which can be written as x to the power of 3n would be a perfect cube. Entire radicals to mixed radicals. Write the radicand, the number underneath the radical sign, as a product of a perfect square or a perfect cube and another number. So if we have the square root of something, we want to write that as the square root of a perfect square times the square root of whatever other number we need. And if it's the cube root, we want to write it as the cube root of a perfect cube and then the cube root of whatever other number. Then you can change the perfect square or perfect cube into a whole number along with a radical. Note, what we started with is called an entire radical, meaning the entire number is under the radical sign. And what we end with is a mixed radical, a number that contains a whole number and a radical. Change the following into mixed radicals. The square root of 20. We want to look at our list of perfect squares. What's the biggest perfect square that can divide 20? In general, the biggest number that can divide 20 would be half of 20, so 10. And that's true for all numbers. The biggest number that can evenly divide any number would be half of that number at most. So you would never look at any number that's bigger than half of your number. So our options here are 4 and 9, because those are the only perfect square numbers that are less than or equal to 10. Does 9 divide 20? No, it does not. Does 4 divide 20? Yes, it does. What do we get when we divide 20 by 4? We get 5. So we write square root 20 as the square root of 4, which is a perfect square, times the square root of 5, because 4 times 5 equals 20. What is the square root of 4? I'm going to bring up my calculator, although I'm sure you should all know that the square root of 4 is 2. Square root 4, 2. So our mixed radical is then 2 times the square root of 5. The whole reason that we have to pick a number from the list of perfect squares to divide 20 is so that we can then take the square root of that number and get a whole number. B, square root of 12. Half of 12 is 6, so the number in the perfect squares that we're looking for has to be 6 or less. The only number in the perfect squares that is 6 or less is 4. Can 4 divide 12? Yes, it can. We get square root of 4 times square root of 3 because 4 times 3 is 12. We can take the square root of 4. It equals 2, so we get 2 times the square root of 3. Square root of 32. Half of 32 is 16. Our number in the list of perfect squares has to be less than or equal to 16. Well, we actually have the number 16 in our list, so it's going to be that one. Square root of 32 can be written as square root of 16 times the square root of 2. Square root of 16 is the whole number 4. And then we have our square root 2 left over. So the square root of 16 is equal to 4 times the square root of 2. Let's do some cube roots. The cube root of 16. Now we want to look at numbers in the perfect cube list. Cube root of 16, half of 16 is 8, so the number can't be any bigger than 8. Well, 8 is our smallest perfect cube, so it's going to be that number. We write it as the cube root of 8 times the cube root of 2, because 8 times 2 is 16. We can take the cube root of 8, math number 4, and then 8 gives us 2. So we get 2 times the cube root of 2. You got to remember the little 3 for cube root. 54, let's see, 54 divided by 2. Okay, half of 54 is 27. So our number from our list of perfect cubes has to be 27 or smaller. Looking at our list of perfect cubes, there's two numbers, 8 or 27. So we know it would be 27 because that is exactly half of 54. So we write it as the cube root of 27 times the cube root of 2, because 27 times 2 is 54. The cube root of 27, math number 4, 27, enter, is 3. So we have 3 times the cube root of 2. 2 times the square root of 27. 27 divided by 2 is 13.5. It's a square root, so we're looking at our list of perfect squares at numbers that are no bigger than 13.5. So the only two are 4 and 9. Can 9 divide 27? Yes, it can. So we write this as 2 times the square root of 9 times the square root of 3, because 9 times 3 is 27. Then we can take the square root of 9. It's 3. So we have 2 times 3 times the square root of 3. And then we can multiply our coefficients. 2 times 3 is 6. And we have the square root of 3. So 6 square root 3 is our mixed radical. A few more of that type. 3 times the square root of 40. Half of 40 is 20. So we're looking in our list of perfect squares for numbers that are 20 or smaller. I have 4, 9, and 16. Can 16 divide 40? Well, you just check. 40 divided by 16. No, it doesn't divide evenly. Can 9 divide 40? 40 divided by 9. No, it doesn't divide evenly. So it's going to be 4, which gives us 3 times the square root of 4 times the square root of 10. We can take the square root of 4. We get 3 times 2 times the square root of 10. 3 times 2 is 6. So we have 6 square root 10. 7 times the cube root of 40. Half of 40 is 20. So we want to look in the list of perfect cubes for numbers that are less than or equal to 20. And the only one that we have is 8. Does 40 divide 8? It sure does. 40 divided by 8 gives us 5. This becomes 7 times the cube root of 8 times the cube root of 5. The cube root of 8, math, number 4, 8, enter. We get 7 times 2 times the cube root of 5. 7 times 2 is 14. We get 14 times the cube root of 5. Last one of this type, 5 times the square root of 200. Half of 200 is 100. So we want to look in the list of perfect squares for numbers that are 100 or less. And we see that actually the number 100 is in the list, which means that's going to be our number. We write this as 5 times the square root of 100 times the square root of 2. We can take the square root of 100. We get 5 times 10 times the square root of 2. 5 times 10 is 50. And then square root 2. Going the other direction, from mixed radicals to entire radicals. To do this, we follow the steps we used above, but we go in reverse. Change the following into entire radicals. 5 times the square root of 7. If we want to put 5 under the root sign, we have to put it to the power of 2, because to take it out, we square root it. So to put it back in, we put it to the power of 2. We then get the square root of 7 times 5 squared, which is the square root of 7 times 25, which equals 7 times 25 is 175. Square root of 175. Four times the square root of 3. If we want to put 4 underneath a square root, we need to put it to the power of 2. Then we have square root of 3 times 4 to the power of 2, which is the square root of 3 times 16. 3 times 16 is 48. We get the square root of 48. 3 times the square root of 5. If we want to put 3 under the square root, we need to square it. We get the square root of 5 times 3 to the 2, which is the square root of 5 times 9, which is the square root of 45. 2 times the cube root of 5. If I want to put 2 under a cube root, think about the ones we just did. Putting a number under a square root, we had to square the number. So putting a number under a cube root, we need to cube it. We get the cube root of 5 times 2 to the power of 3, which equals the cube root of 5 times 8, which equals the cube root of 40. Three times the fourth root of 6. What power are we going to have to put the 3 to? To the power of 4. Then we have the fourth root of 6 times 3 to the power of 4, which equals the fourth root of 6 times 3 to the power of 4 is 81. 6 times 81 gives us 486. We get the fourth root of 486. 2 times the fifth root of 10. To move the 2 underneath, we need to raise it to the power of 5. We get the fifth root of 10 times 2 to the power of 5. 2 to the power of 5 is 32. Fifth root of 10 times 32. 10 times 32 is 320, so we have the fifth root of 320. 3 times the square root of 40. We're doing the square root, so it's 3 to the power of 2 to move it underneath, which gives us the square root of 40 times 3 squared, which is the square root of 40 times 9, which is 40 times 9 is 360. Four times the cube root of 40, move that 4 underneath, you got to put it to the power of 3. We get the cube root of 40 times 4 to the power of 3, which is the cube root of 40 times 4 to the power of 3 is 64. And then cube root of 40 times 64 is 2,560. Last one, 5 times the square root of 19. Move the 5 under, we have to square it. Gives us square root of 19 times 5 squared, which is the square root of 19 times 25, which equals 19 times 25 is 475. That is a review of what you learned about radicals in Math 10C. You need to be able to apply these concepts to this unit in Math 20-1.